Making up just 1% of the Earth's land area, deltas are nevertheless home to more than 500 million people, all of whom are living within 5 meters of sea level. These economic and environmental hotspots are some of the world's most delicate and vulnerable natural systems, facing challenges from resource exploration and climate change. But deltas are sinking 4 times faster than average sea level is rising. The causes for this are by no means well understood, but high-resolution surface elevation models are putting new weapons into scientists' hands as they study deltas and help bring to these vulnerable areas and to the people who live in them some form of help. So to tell us more about this today is Professor James Syvitski. Professor Syvitski works at the forefront of computational geosciences, sediment transport, land-ocean interactions, and Earth surface dynamics. So there you have it. And has won numerous awards for his efforts. He's received a PhD in both oceanography and geological sciences, seems a little greedy, at the University of British Columbia, and has since held a variety of appointments within Canadian universities and the Geological Survey of Canada's Bedford Institute of Oceanography. He presently holds faculty appointments in geological sciences, applied mathematics, atmosphere and ocean sciences, hydrological sciences, and geophysics. There is no end to his talents. As a result, James has over 500 publications to his name, including a staggering 65 books, and serves as an editor for many international journals. Ladies and gentlemen, please welcome Professor James Syvitski. Thank you.
It's a pleasure to be here, and the Geological Society is one of the most outstanding societies in the world. So today I'd like to tell you a little bit about a problem that I think is underappreciated, that there's a lot of people living on these deltas and they're sinking, but they're sinking not because of the sea level just going up, but there's other reasons, and humans are contributing to those reasons. So let me tell you about the importance of deltas. They are, as Ted said, home to lots of people, over 500 million. They have extreme high productivities. They are biodiversity hotspots. They provide transportation systems to those that live on them. They filter, they're the repositories for, and they're the reactors of fresh water, sediment, carbon, nutrients, and they filter out the pollutants going into the ocean. They are home to almost all of the megacities that have grown in the last 35 years. They're ports of entries, of course. They're centers of forestry, fisheries, and aquaculture. And they're considered the rice bowls to the world. But they're under threats, and I'm going to walk you through some of these threats. The one that I'd like you to leave with is that we often mine these deltas for the groundwater, the fresh water that they contain, also the oil and the gas that they contain. And given that, with not getting any more sediment, or nearly as much as they used to, they are now sinking. But we'll go over some of the other threats too, and the consequences that these threats have placed on the people living in the deltas. And some of them include that the soils are going salty, and you can't farm there anymore. So as rice bowls, that's a big problem. Fisheries are a major stay for the people who live on them, and they're collapsing. So we're going to go through some of these in a few slides. I don't have too many slides, but I picked here 4 deltas for you to look at. The Nile, the Indus, the Ganges Brahmaputra, and the Mekong. And where you see dark brown, that's where heavy population inhabitants are living. The red you see is urban extent, and you can see these cities. In fact, if you look at the Nile, it's home to almost 50 million people on one delta. If you look at the blue, or whatever color that is, that's proportion of the delta surface that's cropland. And Showing up in brown lines is the roadways across these deltas. So these are just 4, and there are many dozens of deltas around, big deltas around the world. So we can say the human footprint is large. So let's look at one of the first changes. Discharge. This is the water flow to the delta from a major river. And if we look at the Nile, this is what happens when you build a large dam. You take out the high discharge flows. And so now this is the discharge record after the Aswan Dam was put in. You'll notice that the low flows go up, the high flows go down, and you get a rather boring discharge record. And this is the number of years, and this is the magnitude of the water flow. So in this case, we've made an active river that used to flow across the delta, bring nutrients with carbon and sediment to the delta surface. That's no longer going on anymore. That's what a dam will do. And if we look at this map, this is the stored runoff, and we're storing more and more of the water that used to go to the ocean in these reservoirs and delaying their flow to the ocean. So that's another consequence is once upon a time the water would get there, it would become part of the ecosystem. Fish would use the nutrients from this water flow, and now the water is getting to the ocean at a much different time and in a different geochemical capacity. This is a map of Thailand. This is the area. Bangkok is major city down here, and this is the flooded area from 2011. So this whole area, hundreds and hundreds of kilometers of land were flooded. Now floods occur. It's not like this because there's a dam. This is limiting the floods. In this case, the operators of the dams in Thailand, they were really worried about precipitation. And so they were so worried, and the reservoirs were so high that they released the water much too fast. And all of this flooded area was because they released the water too fast. Same kind of dam, different way of dealing with this kind of threat. So this is a picture of the Nile. And if we look at ancient maps, and in these different colors, these are the distributary channels, the channels from the Nile that fan out across the delta, just like over on this side of the room where there's a picture of the Lena Delta. Here, these distributary channels would migrate across the delta. They'd migrate across, they would deposit sediment, nutrients, and you can see 1813, 1831, 1897, 1922. They built the Aswan Dam right around here, and almost all of these distributary channels disappeared. They were replaced by canals. So now we have a very artificial system. And we have very few channels that cross this. That's good news in some cases, because now these 50 million people are no longer getting flooded out. So that's the good news. The bad news is the delta is no longer getting natural nutrients, and it's not getting sediment. And you'll see why that's important in another slide. Another change in discharge flowing to the ocean could be considered in this diagram. This is a water balance diagram for the Indus, for the Sindh province that's just on the landward side of the Indus River in Pakistan. And where you would have 108 units flowing down to the ocean, this is in cubic kilometers, much of that water that used to get to the sea no longer gets there. It doesn't get there because it's getting diverted to fields, croplands. It's getting evaporated the plants themselves that are growing are putting it back up into space. So by the time it gets through the farmlands, there's very little water left. In fact, this was in 2003, the value's gone down another 50%. This map by a colleague of mine, John Milliman, shows that in red are the river delta systems where the discharge has decreased by more than 20%. So there are some areas where the water is going up, and that in the Mississippi case, it's because water that was flowing to the Pacific is now being diverted across the mountains into the Mississippi and then flowing into the Mississippi. So we're changing nature and how it puts water out there. But water, rivers, also bring sediment. And in circa 1700, this is the best estimate we have on how much sediment would get to the ocean. So the size of the dark box is an indication of the millions of metric tons per year on a scale of 0 to 400. So there was a lot of sediment getting to the Gulf of Mexico from the Mississippi River, around 430 million tons of sediment per year. But this is what it was in the 1980s to 1990s. You'll see many differences. First off, the Ohio River didn't really add any sediment. But because of deforestation, agriculture, road construction, and other human activities, a lot more sediment comes from the Ohio River than it used to. Because of dams, there's not much sediment leaving the mountains of the Rockies and getting into the Missouri River and going down. And I'm going to show you two movies that I call my Matrix movies, if you've ever seen that film. So the first one is of the United States, and it's from an inventory that positions every major reservoir in the US. So here we go, and you're going to see this date, you're going to see this date move, and that's the year. So in 1800, as far as we know, so you see where the population was in the 1800s, and then it's migrating to the west. Just so you don't think this activity doesn't go on worldwide, we're going to look at another movie. This one is The World. Now, here's the difference. The one for the world, because it would just turn black if I didn't change the scale, we're only going to look at the extremely large dams. Okay, so you won't see nearly as many in the early days as you saw here, for instance, in the US. Every time it turns red for that year, that's a new dam. And so you'll see red blink at you. And then it'll go blue. In 1945 or 50, look at Mao Zedong in China. Little preview. So you see the British Empire, Australia, New Zealand, India, Japan, Korea. There goes China. Are we changing how river systems work? The answer is yes. And there was a lot of sediment that used to get to the coastal oceans into the deltas that no longer get there because of these dams. So here's a little delta. It's an interesting story, the Ebro in southern Spain. So this delta used to get, in the 1913 to 1962 period, a lot of water, 1,732 cubic meters per second, and a lot of sediment, 576 kilograms per second. Now here's the thing. The amount of sediment that it used to get was created by humans in the first place through deforestation. We created the delta. The delta didn't exist a few hundred years ago. So we created the delta, then we dammed the delta, the river system, and now it gets much less water, goes up into evaporation through the crops, and we get almost no sediment. Consequence, they're trucking millions of tons of sediment to the shorelines of southern Spain. In fact, there's a salt mine here, and this keeps getting washed over, so they keep trucking sand to have the trucks reach that area. The Dutch government also spends a lot of money, over 100 million euros on an annual basis, and they truck about 100 million tons, and they use some shipping dredging system to also replenish the sediment on the shores. This delta is 26% of the entire nation is below sea level, protected by this sand that they're trucking to the shores. So on the sediment delivery story, here's a delta, the Po in Italy. This delta wouldn't have existed if it wasn't for humans again. It was created basically by constraining the movement of the river system because the Venetians did not want the Po to flow into the lagoon and fill up the lagoon. It was a military decision at the time. And so you have a delta that we created. The Yellow River is only 150 years old. It used to flow into the Yellow Sea. Now it's flowing into the Bohai. And again, this is something that we created largely because they were farming in the Loess Plateau of China, where it's easily remobilized sediment, and this sediment poured onto the system. Now it's under threat. And we talked about the Ebro. So we created many of the deltas, and then we're now destroying them simply because we no longer supply them with sediment. But the story is not simply a sediment deprivation story. Aggradation is the rate that sediment is added to the surface of a delta as a new sediment layer. And typically these rates are less than 50 millimeters per year. But up to 50 millimeters per year is many times more than sea level is rising. Sea level rising, even with global warming, is only going up this much a year. Only going up between 1.3 in the 20th century, and in the 21st century, it's now at 3 millimeters per year. So certainly a problem. But if we were adding sediment to these coastal zones, that would be much less of a problem. There's some natural compaction, there's organic matter, sediment gets jostled around and more compacted with time. And so typically you add sediment and then you compact it. So both of those are natural. And if on the really big river systems, just the weight of these billions of tons of sediment is enough to press down and move out the crust, the asthenosphere, and that's called load isostasy. And you can get a little bit more subsidence in those conditions. But the story that I want to tell you about is this accelerated compaction. This is the mining for petroleum products and the mining for water. If you look at these numbers, this number is the largest number on the board. And that is something that we're doing. So here's a simple equation. The rate of sea level change is equal to how much sediment you add, what's going on in the ocean in terms of sea level rise, this natural compaction, human activities related to compaction, and some other geophysical term, M. If we keep these two the same and natural compaction the same, we say that in some hypothetical delta, this is a 13 millimeter per year change. And we've cut down the aggradation in half, and we now have sea level rise. You can see you easily tip over from an area where, under natural conditions, the delta is growing to a time when you're actually getting sea to win in the story. So let's look at this in a little bit more detail, this relative sea level. So Bangkok went from 1 million to 12 million in 35 years. To survive, to do their crops, they needed to pump a lot of water out of the soil and use it for their agricultural purposes. That created subsidence levels of up to and over 100 millimeters per year, 10 centimeters per year. So remember, even today's accelerated sea level rise is only 3 millimeters. Here we have 100 millimeters per year. We're having, I mean, if you've gone to this area, it's just incredible, the subsidence rates. And as a consequence, the shoreline is retreating rapidly, over 1 kilometer in less than 25 years, or a little over 25 years. And we know something else. In fact, countries know this. This is not something that I'm telling you and no one knows about it. Everyone knows about this. And so they're trying to weigh how much can they pump out of the ground to win versus the harm they do in terms of subsidence. It's a cost benefit. In Italy, if we go back to the delta, the Po delta, they were mining this delta for methane. It was sinking, their subsidence rates were 60 millimeters per year. Venice, which is just north of here, they were again upset that the whole area was sinking, and they knew why. They stopped the mining for methane. And not too long after, the rate went from 60 to a high of 20, and now that some time has passed, it's gone back to ambient conditions, 4 millimeters per year. So there's an example. A problem was known, somebody did something about it, and they stopped it from sinking further. But even though this is known, and it's been known for years, I still look around the world with my tools, the satellite tools that I have at my disposal, and I see all sorts of crazy stuff still going on. So let me tell you about one example, the yellow. The yellow delta has quite a number of oil fields. They're pumping out 33.6 million tons a year in crude oil. Okay. And we are now using satellite systems that has the resolution of 1 millimeter per year. It's a high resolution. We can look down and see whether a land surface is sinking. And we get these bullseyes, which are telling us, in this case, between two images, spring 2007, it sunk 5 centimeters in 70 days. Here's another one, 2007, 2008, 6 centimeters in 70 days. And we're getting rates of 240 millimeters per year. So remember, sea level's going up 3 millimeters per year. Here we are sinking at huge values. And what's under the bullseye? In this particular case, 200 oil pumps. As a consequence, they've had to build these huge seawalls out of cement, 38 meters wide at the bottom, just to allow the sea from not penetrating the land surface. So obviously they know what's going on. It's not a surprise to them, but they're they're weighing the value of pumping the oil up versus the delta getting below sea level. In Jakarta, this was sent to me today by colleagues in Del Terrace in the Netherlands. Jakarta is sinking at rates equal to that of the yellow. And here we have areas of Jakarta that are now 4 meters below sea level. And of course, the Dutch are involved because it's very similar to what has gone on in the Netherlands. So we're having areas where 500 million people are living that are sinking rapidly. So if we looked at the 20th century, so 1900 to 2000, sea level's been going up at around 1.8 millimeters per year. Before that, before global warming took off, it was rising only less than 0.5 millimeters per year. So it is accelerating, and in the last couple decades, it's going up around 3 millimeters per year. But still, look at what's happening on the deltas. They're sinking on average around the world 4 times faster than sea levels going up. This is looking with satellites at some deltas. It doesn't really matter where they are, but this is an example of, we've analyzed the entire world's deltas. And anywhere you see pink, like this is a delta in Poland, the Vistula, it's below sea level. There's that yellow delta we were looking at. In some deltas, of course, things aren't so bad. In other deltas, they're much worse. Another side effect is land use. So there used to be kilometers and kilometers of mangroves around some of the tropical deltas. And these mangroves would be very effective in slowing down a storm surge from some hurricane, cyclone, typhoon. So I'm going to show you a picture in 2001. Keep this distance in mind. This is 250 meters. You're looking at Thailand. These are shrimp farms. The thing about a shrimp farm is that it has to be extremely flat because they have to store water for the shrimp to grow. They cut down the mangroves to put these shrimp farms in. So I put a red line on the image for 2001 for you to see. So just a few years later, this is the land retreat. So that's another side to the story. It's how we use the land. So you can imagine when this was published in Nature Geoscience and other papers, the newspapers picked up on this big time. And, you know, with all the interviews and things like that. But the Chinese picked up on this, which is the Pearl Delta. So there's a lot of people. Hong Kong, for those of you who know it, is just underneath this area here. But this is the Pearl Delta that flows into this bay. And if we looked at the population here, it's, I don't know, something like 25 million people. And so a lot of this is urbanized, and they built these large storm surge walls to protect the city. So my prediction is, because this area does get hit by the odd typhoon, that this is a disaster waiting to happen. So I'm out there on a limb predicting something. I hate doing that, but I did it. So watch where you go on vacation. And I say that because our experience in the US with Katrina, with metal, cement, we thought we did everything, and of course, nothing is perfect. You can never engineer everything perfectly, even though some people claim you can. And that's the problem. There's always some weak link that allows water to get over. In the tsunami at Sendai, the water Because of these walls, once the water's in, it takes forever to come back out. And so that causes even more damage. And most of the damage in New Orleans was because the water never drained away. So we now map the world's surface, the entire land surface, twice a day for floods. It's part of the organization that I run. It's called the Dartmouth Flood Observatory. And this is a product, and this is for a number of years. This is Mekong, and this is the flooded area. And we look on the land surface just to see where floods are. And here's Thailand and the Chao Phraya River going through Bangkok. But because of what we're doing, we know that the magnitude and the frequency and magnitude of floods are increasing. And if you looked at the numbers, we took 33 deltas and we did the calculations. 260,000 square kilometers was submerged in the period from 2001 to 2008. And remember storm surges. Storm surges, mostly because of wind, a little bit because of the air pressure, but mostly wind, it's moving a wall of water towards land. And this wall, the height of it depends on the strength of the wind. And so you can get 1 meter, 3 meters, 5 meters. You can even get a 10-meter storm surge. So if you build a wall that is protecting you 3 meters above sea level and you get a storm surge that's 6 meters, the wall is not doing you any good. So here's an example in, this is Hurricane Nargis. This is the Irrawaddy Delta in Burma, or whatever it's called these days. Myanmar, yes. So everywhere you see in red is water that came ashore from the hurricane. This was a delta that I never thought was at risk because of subsidence. The human activity on there is minimal. There's lots of cities, but they're just not as using it in an industrial level compared to other areas. So the land surface is all above sea level, yet the storm surge just inundated, killed over 200,000 people. This is, wherever you see a red star, was a big delta that we used in our study. This is the hurricane pass over the last 100 years. So there are some deltas like the Amazon or the Orinoco that don't get any hurricanes. So the southern Atlantic is almost hurricane free. But for most of the large delta regions of the world, they get hit by hurricanes, and therefore they're affected by these storm surges. And when we look at where the heat on the ocean is, the area of warmed ocean is increasing in size, and typically you scale hurricane intensity with the warmth of the ocean. And so there may be not more hurricanes that are going to happen, but the ones that do happen will likely be bigger. And bigger is bigger storm surges, which is a problem for deltas. So, the person who published this in the U.S. Geological Survey, they got into trouble. They were looking at land loss. So that's not where they got into trouble, but they were looking at land loss between 1932 and 2000. This color orange on this map, there's New Orleans is someplace over here. This is the Mississippi River. This is the width of the image is 300 kilometers. This is the land loss. And they were mapping it out sequentially. And it just so happened that there was a really good correlation with gas mining. Well, you can imagine that the oil companies didn't want to admit that they had any role to play in this story because of, in the US, everyone sues everyone. So, so that part didn't go anywhere. But this is a major problem. The land there's major land loss. So remember this story is either it's not getting new sediment, which is a big problem, or it's subsiding, or the sea level's going up. Those are the factors that are affecting this story. And it really doesn't matter whether we're dealing with a tropical delta and they're pumping water out of the ground like Shanghai. Shanghai was sinking at an enormous rate before they realized the city was falling into the ocean, and they stopped pumping the water. You get stories like this, and this story that was published in Nature Geoscience, Mike Bloom, he's from Exxon. So it's not like nobody knows about this. This is today, 2009, and here's what he's suggesting the Mississippi Delta is going to be like in 2100. Now, this is a big problem for the oil industry. The infrastructure in, dare I say, trillions of dollars along here, the refineries, is something like you can't find anywhere else on Earth. It's literally controls the gateway to the power supply for the US. So it's important to know what's going to happen by 2100. We go back to this picture, you'll see these deltas are as new land. And that's true. There was a new diversion, and the Atchafalaya Wax Lake deltas showing up in green was new land. So the idea was, well, maybe we can open up areas to create new land in other places that would protect it. Mike's story is, can't be done. That yes, you can create new land like these Wax Lake Delta areas are new, but they're just too small to protect a delta this size. So I'm going to show you a sneak preview of a movie. It's not really about deltas, but it's going to really hopefully give you a sense that humans are really good at taking over planet Earth. They have the odd problem, though. So here we go. Enjoy. And it's going to begin with the Industrial Revolution in the UK. people live, we have a large footprint. That's a sneak preview of a movie that's coming up. Okay, so life at the edges. I'm going to leave this up, and I would like to take this as an opportunity just to answer questions. This is what I talked about: changes in sea level, sediment delivery, discharge, shorelines, land use, and storms. And if you have any questions, I would be happy to field them now. Thank you. Yes. Okay.
You don't want to break my rice bowl here. We'll do the usual thing. I'll take questions from this, and then that, blocks. But I have to warn you that James has to be away for a television interview on the dot of 4. So I'm going to be marching him out of here on the dot of 4. So there'll be no questions after that, I'm afraid. So we'll try and get them as many people in as possible. So if we could take them from this section first. Gentleman in the middle there.
So the question is, will global warming impact rainfall and therefore runoff? So in general, warming of the atmosphere will intensify evaporation and increase rainfall. It's way more complicated than that. There's going to be areas of the world where it'll be much more of a desert, and other areas that'll get a lot of rainfall. But on average, if you took the entire globe, it would be more rainfall. Okay, so the question is, what's the impact, positive or negative, on sediment being retained in the dams? So there is both positive and negative, like everything. One of the things is that these dams now sequester carbon. And so instead of being oxidized and going into the atmosphere and further contributing to our problems related to global warming, some of it is being sequestered and stored in the dams. So that's good news. And as you know, the reason we build dams is for a lot of great reasons. So I don't want to go into that. You all know them, hydroelectric power being one. But the interesting thing about these dams is that there are old dams and new dams. Old dams are bad, new dams are a little better. So, and the new dams, you saw in China, they're the ones with all the new dams, and they've been building them a little better than we did 150 years ago. So they allow sometimes sediment to pass through them. So they're not storing, so not all the sediment is stored in the dams. But here's the thing, around the world, in almost all cases, the people who've done the estimates to how much sediment will be stored in the dam have underestimated the rate. And because they've not estimated that properly, they would say that the life of this dam is 150 years when in fact it's turned out to be 75 or 50 or 25. So they got that wrong. The dams are filling up now. And so you've got two choices when that happens. Number one, you have to then mine the sediment to increase the storage capacity. That's very costly, but they can do it. And number two, they have to build another dam someplace else to generate hydroelectric power for whatever reason the dam is there. So that's the problem today.
Right. Looking at change in relative sea level at 0.3 meters a century, that of course is worldwide. Is your figure of 1.2 meters a century average over the whole globe, or is it just for delta areas alone? In the middle.
It's just for deltas alone.
Right. So in fact, it's more like 0.2 meters per century.
In fact, if you looked at the tidal gauges on either side of a delta that maybe were put into rocky areas, they're just showing the normal global sea level rise. It's only when you look at the tidal gauges in the softer sediments of the delta themselves that's where they're accelerating.
That's in fact what I've found as well. Thank you.
What is the future of Bangladesh, the whole country?
Okay, so obviously this has been a discussion in this audience before. So there's a lot of unfortunate things that have hit Bangladesh. So when they get water, they get a lot of it, and huge areas are flooded during the monsoons. But when it's dry for month after month after month, and they're pumping water out of the ground for the crops. Problem there is that it's really unfortunate that water is also filled with arsenic and other things. So that's hurting, killing people itself. The delta is sinking for many reasons and at rates probably as great as anywhere on Earth. There's some of the reasons are just pure geology, geophysics, tectonics. It's just sinking. But in many areas of the Indian side of the delta is basically getting no flow anymore, so it's just sinking rapidly too. So it's a very unfortunate story, the bank.
The sinking of Shanghai a reversible act, or will it just stabilize?
I'm so glad you asked that question. No, this is a terrific question. And you know, I think scientists should never guess. They should experiment, right? That's what they should do. And it should be a testable experiment. So we're actually quite used to pumping things back into the ground. Secondary recovery in the petroleum industry, that's what that's all about. So we have experience in putting things back into the ground. The question is, can you put enough in, whether it be gas or liquid, to pop it up? I mean, that's a good question. And so the one experiment that I know about was in the Houston area where they tried that and it didn't work. So when you pull out deep down, the fractures are going up through so many different layers. It's collapsing the entire structure. And then you have basically a structure that is connected to the surface, and it's leaky. So you can't put things in, and even at really extreme high pressure, if you had the right nuclear reactor or something, you can't pump it back up. So that was the experience at Houston. Long story short, no.
Okay, are there any more questions from the central block, please?
All manner of geological events are supposed to result from fracking. Is this an analogous situation?
This is also new that I'm not the world's greatest expert on that. So fracking is putting something in and taking something out, and it's designed to crack the rocks. So I think I haven't really taken our satellites and focused it on Pennsylvania, That's where I would at first, in Pennsylvania, where it's probably at its most extreme and it's shallow and likely would create subsidence. So that's a good target to look at. We do a lot of fracking where I live in Colorado, but that's quite deep down, and I don't think that would show the same magnitude of subsidence as it might be in Pennsylvania. And I'm not sure about fracking in other parts of the world. I basically only know what's going on in the US in that story.
A brilliant analysis in your lecture and fascinating visuals, but the message you appear to be giving us is that nothing can be done. Is that the case?
Don't contribute to it would be lesson number one. So when Shanghai and they were sinking and they stopped, well, basically they dialed back the amount of groundwater they pulled out of the ground in that area. They noticed each time they ratcheted down the amount of water coming out, the land sank more slowly until they thought they were at a place that they could live with. They still needed the water. That's an economic vitality for the area. You wouldn't think so, but it is because of the pollution in the river. But so, you know, each country is doing this cost-benefit analysis, and there's no one big answer. But being aware, dialing it back, and not contributing would be the first line of attack. The second one is the sediment. How do you get sediment on the surface back again? You know, around river systems, they flood and farmers move into the areas that would flood and move out on a regular basis. Deltas are much bigger, they're hundreds of kilometers, so it would, and there's cities there. So whether you could put barriers around the cities and have farmers move in and out and flood the area and get new sediment onto the surface, that may preserve them. So that would be another option that people are talking about. Making sure that you have the barriers in place that are effective. Don't cut down the mangroves and things like that. I mean, so there are some things that may not reverse it, but could not contribute to the problem and should be done.
You said that Chinese dams were rather better than the old ones. Is there continuing research that might improve dams still further so that it would allow more sediment to go through?
I either alternate between a doomsayer and a Pollyanna. It's hard to get that middle road. You know, a lot of the European and American construction companies that deal with dams, they've been more concerned in the last 15, 20, 30 years on fish migration. You know, getting the fish in and out of those fish ladders and things like that. So they've not put a lot of time into these butterfly dams like the Chinese have. The reason the Chinese have put so much effort into it, their rivers were so heavily loaded with sediment that they knew that if they're going to spend billions of dollars building a dam, and if they were not effective in letting that sediment pass through, they were literally losing money by letting it fill in. So they had to come up with a system to allow the sediment through. I think that's, well, everyone's still building dams, and they're building dams, and I think there's 29 mega dams going in the Amazon. So that will be another river system that's going to be impacted by this, so they should learn from China.
Mangroves being replanted? Are mangroves being replanted?
Good question. So there's, I was attending a mangrove conference, and they've really come a long ways. They used to put monocultures of one particular type of tree, mangrove. And if that took off, all the trees were in a row. Wasn't very good at stopping storm surges. But they're now literally going along the coast, and they've got these mangrove seed balls that they throw out of planes. And they have about 20 different species. And they may not know which species is going to take off, but because they have so many going in, and they're literally covering the coastal zone, it's turning out to be a very effective way. So in some areas, I would say the answer is yes, they're starting to recognize and deal with that problem. It's quite a livelihood in terms of fish and forestry.
You have mentioned the anthropogenic forces
Yes.
acting to the sediment. You had given different millimeter per years. And my question is, in what way are acting the anthropogenic forces to the sediment?
What ways?
In what way are they acting, these forces, the anthropogenic forces? In what way? In which way?
Well, I think anthropogenic forces would include humans. Anthropocene is human activity, so human activity is mining, deforesting, putting in roads. That creates a lot of sediment. So that's putting more sediment than normal into the river systems. The dams, diversions, things like that are taking the sediment out of the system. And in some areas of the world, the sediment flux is going up. In other areas, it's going down. For the deltas that we're talking about, it's largely in the negative territory.
Thank you very much.
You talked a lot about oil mining and water mining. Is there a role for CCS to put the carbon dioxide back into the land under the deltas?
Carbon sequestration.
Yes.
That remains to be seen. There are hardly any places on Earth where these experiments are going on. There's one in Alberta, one in Norway, and they might help a little bit. It would be much better if we weren't drawing out the deltas, because the peat is getting oxidized and liberating even more carbon. So one of the carbon stories on these deltas is us drawing the deltas out and the peat just burning away in the ground.